Welcome everyone to this talk. I know that lunch is coming up, so I'll try not to stay up here longer than necessary. My name is Marc Klefter. I'm the CTO for a Swedish consultancy firm called Edgement, where we focus on cloud-native app development with an emphasis on message-driven systems. And in this talk, I want to explore access control in message-driven systems, perhaps a somewhat esoteric topic. To start up with, how many of you are message-driven today, say, using pub/sub in any form? A lot of you. How many of you do any type of access control, permission checks, when you consume a message? Fewer, definitely. Okay, so this is what my talk will be about. The actions you take when you want to authorize whatever is going to happen when you consume and process some type of message. So we're going to focus on a specific context, which is zero trust. So we're going to look at what a zero trust environment means and why it's so important to establish a functional access control mechanism in this regard. For those of you who are not familiar with messaging, we're going to explore that a little bit, see what types of messages we are dealing with. And we're going to see how Open Policy Agent helps us to actually enforce policies where we need them to happen. And we're going to finally look at how do we actually implement zero trust for asynchronous communication, that is messaging. And hopefully we have some time left for Q&A at the end. So I want to start by setting up a frame of reference for this talk. What are we going to use as a foundation for this exploration? First of all, access control, that is authorization. So we're going to assume that we have some sort of verified identity to work with, meaning a user or some system has provided credentials, we have authenticated them, and we've received a token, or rather the user or the system has received a token, which then will provide us for access control. So in a general sense, we're going to use this verified identity in the form of a token. Most of you are probably familiar with the notion of JSON Web Tokens. I'm going to call them tokens for short. And they will help us to enforce that this particular verified identity can perform some type of action on some type of resource. And we're going to use a model called attribute-based access control because it gives us the most flexibility in coming up with a decision. Can we perform this operation or action on a resource or not? Tokens usually contain claims, attributes that we can use. Resources could do as well. And we can also use perhaps some environmental attributes. All of it factors into the decision, do we permit or deny this particular action? Furthermore, the type of system we'll be studying is a distributed one of services, or microservices, if you will. And our aim is to take this verified identity and all of the claims therein and propagate it along the synchronous flow that we'll set up to perform the type of business logic that we desire. So this identity context needs to be available at every touch point along this flow. So I mentioned asynchronous communication. That is the cornerstone in this talk as well. So it means that services do not interact directly with each other. Rather, we're decoupling them and we're using some type of intermediary, here called a message broker, to facilitate the interaction between services. So with this as a baseline, let's look at what zero trust entails. You might be aware of the old adage, trust but verify. This is sort of the stricter version of that, where we go with never trust basically anything, always verify. Sounds great in theory, can be hard to implement in practice. But it means that we are no longer content with only enforcing access control at a network boundary. We're assuming that anything both outside the boundary and inside the boundary is by default to be untrusted. Like a real-life example of this is your Wi-Fi network at home or even in your office. A friend or colleague might stop by and ask you for the Wi-Fi password. You, of course, are friendly back, so you provide them with this password, and they enter your network. In a lot of cases, we're fine with that. We're trusting this particular person to operate within our network. But do we have any idea what the application on the particular person's machine do? Seldom. So for modern use cases, this is not enough. And we have this divide between application security and network security. As application developers, we have one notion of what it means to secure our applications and interactions. But the IT department that deal with network security at a lower level, they have a different notion than we do. So this gap between different departments and different philosophies and policies create trouble sometimes. For example, you might have a Kubernetes cluster administrator assuring me that yes, access to this cluster is fully secured. I've done my job. But it turns out that for some reason, the services that are operating within the cluster are exposed to the outside world. Yes, this can happen and has happened. So yes, your cluster might be secure, but it turns out you missed a couple of things because the application developer, when writing the Kubernetes manifests, didn't really agree with what the network administrator or the cluster administrator had in mind. And in this modern age, we're dealing with a number of threats inside of our network boundary. Its breaches are not uncommon. We're dealing with malicious applications both externally and internally. And it's always our fault, so to speak. We might be using third-party open source packages. And how many times have you seen a particular NPM package, for example, highlighting certain vulnerabilities, supply chain attacks, and so forth? We're not always aware of everything that might be malicious that we embrace in our applications. So we desire some type of zero trust philosophy and the implementation of it in our applications and our networks. Now, this is hard to implement sometimes, and we must make sure that implementing zero trust, the cost of it doesn't exceed the value we derive from it. In practical terms, it means that sooner or later you will have to work with your network security people. But we as application developers should make sure that we have done our part to ensure that along every step in our asynchronous communication, we are as sure that we can be that we're not trusting or assuming anything, but rather making sure that our access control follows the principles of zero trust. So this talk is about messaging, that is asynchronous communication, but it can be helpful to look at what synchronous communication entails and how zero trust might shape up in this context. So in this slide, we have an API gateway. We're assuming here that some client has been authenticated, provided with a token, which is then passed to us in the gateway. Now, tokens, they have this nice property of being stateless, or they can be used for stateless authorization. We don't maintain any sessions when we're using tokens, which is nice when we try to scale out our distributed systems. So this token is provided to the API gateway. We validate the token, and now we're inside the network boundary. Again, we're trying to follow some zero trust principles. We start by making a token exchange. That is always a good practice. So we take the client token, and we exchange it for an internal token with the client information, from our authorization that we authorization server that we definitely trust. That we have to have some trust in some things that we deploy. The authorization server is one such entity. So this token can then be trusted by all services that operate inside the network boundary. So this exchanged token in pink is then passed to a first service, a backend for frontend, if you will. And that service, in turn, calls another service using that token. So here we have two layers of security. We have the network part, which is illustrated by the blue arrow labeled MTLS. Have you heard of mutual TLS? Some of you probably have. It means that each service, the BFF and the service that it contacts, can be mutually authenticated. The client will trust the caller will trust the callee, and vice versa. This is often what we deploy or enable in a service mesh inside of a Kubernetes cluster. That's on the network layer. But we, on the application layer, also provide the token that is to be used inside the network boundary. So it's always good to have as many layers of defense as possible, and we're making sure that we have that at two different levels in this scenario. Now, synchronous communication implies short-lived interaction. These tokens shouldn't live for very long, because if this call and this call chain fails, then we're done. Or if it succeeds, we're done as well. So it's a pretty simple interaction style. So what happens if we make a slight change, if we need to have asynchronous communication in this scenario? For example, let's say that our backend for frontend now, instead of calling a service directly, calls it indirectly through a message broker. Imagine that the API that we support externally is asynchronous as well. You can post something to the API, you get an immediate response, and then you can poll the API for a result, for example. In either way, we, in the backend for frontend, we post a message or publish a message onto a message broker, and sometime later, our service will consume it and process it. Now, this is different because this interaction is typically not short-lived. There is a different definition of what short-lived means, but imagine that this interaction is long-lived. Maybe the service doesn't consume the message immediately, it might take some time, or even requires manual intervention, approval from me before the asynchronous flow can be completed. This is tricky and can cause some problems, mostly because the identity context, the JWT or token in pink, there is no intrinsic mechanism for just including it in the message. It's typically lost. That's one problem. Another one is that when using messages, we're implicitly embracing a property called location transparency. When, in the synchronous case, when one service calls another, we know who we call. We know the name of the service we're calling, what the API is, etc. Here, I'm creating a message, I'm putting it onto a broker. I don't really know where it will end up, who will handle it, and how many consumers there will be, in the case of events, for example. So we're being more transparent about where things will be processed and how. We can still use MTLS and ACLs, for example, when publishing to a Kafka broker, and this ACL can control what topics I'm allowed to publish to. Again, we're on the network layer here, but on the application layer, the token is typically lost. Or there's no easy way or obvious way to include it in the communication. So this is where our focus will be for the rest of this talk. So we're talking about messaging. There is not one message. There is roughly 3 different kinds if you're building a message-driven system. First, you have commands. You can think of them as normal requests I've termed them sometimes asynchronous request reply. You send a command to some command handler. You don't know exactly or typically what command handler that will be, but you can be assured that some handler will process your command and return an acknowledgement. Yes, I successfully processed your command. Typically, one command handler will handle commands for a range of entities or resources. But commands are pretty simple. You send them out, they will be directed towards a single command handler processed, and you hopefully will get an acknowledgement back. On the right-hand side, we have queries. Mostly the same semantics, though we have different types of them. You can send a query to a particular destination that you know of, or you can scatter the query and gather results sometimes when you don't know exactly how many query handlers are out there that might have interesting responses for you. And then you have subscription queries where you initiate a query, but it can be long-lived. So you'll get a result first, and then over time you get additional results as they occur. And then we have events, which will be the main focus here as well, because they follow the semantics of publish, subscribe. You have any number of consumers out there, either present or being added or removed in the future. And they typically don't provide any results for you. There is no acknowledgement more than the broker itself telling you, yes, I successfully got your message and delivered it to a consumer. So since commands and queries are roughly the same, well, I'll try to combine the semantics for them in one discussion, and then we'll look specifically at events and what makes them so particular. So let's look at a simple messaging flow where we have one service trying to trigger something else in a different service. So think of this as an operational workload or flow. One service calling another service and triggering some business logic or activity in the other service. We'll start with a command. I'm using here some kind of abstraction. You can think of it as a command broker or command bus. The naming is not really important, but this command is routed through some abstraction we call a bus to a command handler. This will be our first enforcement point. So imagine we have a token, as we'll shortly see, in the command. This is where we'll first have to check for proper access. In response to processing a command successfully, you'll often see an event being emitted as a consequence of processing this command. And this command, again, is routed to one or more event handlers through an abstraction we can call an event bus. And then we have the second enforcement point, the event handler. Once we process this message, we typically want to enforce some policy to make sure that some action that is to be taken on behalf of the user that is sort of tacked on in this flow is permitted or denied. We're still in one service, but now we want to propagate the identity context to another service. So we'll emit an event. This is a subscript with an I, so you can think of it as an integration event. I typically don't like that name, so think of this event as an external event, external to the service, whereas the first event without a subscript is an internal event. And this event, for example, can then be translated into another command to do something in the second service. And then you have your additional enforcement points as well in the second service. So two services interacting through some kind of messaging system using these notion of buses for commands and events and the different types of enforcement points that we can encounter. Again, this is for an operational workload. I'll be talking about analytical workloads in a bit. Now, to provide a little bit of abstraction here, each of these services, you can think of them as, if you borrow some DDD terminology, as bounded contexts, logical groupings of services, one or more services, where the commands and queries are the APIs. to this particular bounded context. Again, it can be one service or many, depending on your, for example, scaling needs. A command typically means that you're updating some type of state in this context, this bounded context. You have internal events that you can use to, for example, update a view of some sorts that you can query for information. Are you familiar with CQRS, perhaps? Then you probably command query responsibility segregation. Then this will probably be familiar to you. And then we have a bounded context emitting an external event to another bounded context, just as we saw in the previous slide. These bounded contexts, you can make an analogy to VPCs. There are logical groupings. But the thing is, inside of this context, the infrastructure we use, for example, for routing commands and internal events, can be completely different from the infrastructure we use between contexts. That is often the case. So here we come to the merging of our responsibilities as application developers and network security administrators. If we can sort of confine ourselves to a bounded context and reassure ourselves that, yes, we're very, very determined to make sure that everything is safe inside of bounded contexts, we can sort of relax our strict, always verify, never trust principle inside of the bounded contexts. It depends on how much it will cost you to implement a fully zero-trust architecture inside of a context, but typically, if we work together, application developers, network security personnel, we'll find a good compromise. However, between bounded contexts, we'll be less sure. So that's where zero-trust principles must typically follow to a larger extent. Now, we've seen that there are a different number of enforcement points where we need to check for access for a particular identity that is propagated along this flow. How do we actually do this? Is there something we can utilize for this purpose? Some of you might be familiar with Open Policy Agent. It's I wouldn't say recent standard or de facto standard, but it's an open source initiative which defines certain elements in an architecture for us to work with access control policies in a straightforward manner. So imagine we have some type of request coming into a service or a context. We'll have one enforcement point, a policy enforcement point. How do we get hold of that actual policy? Well, it's not up to us in that particular part. We'll delegate that to a policy decision point. That's where the actual enforcement will occur. That's where the policy resides. That's where extra data is available to come to a decision. So we, from our policy enforcement point, provide or invoke the PDP to make a decision for us. The PDP, in turn, relies on a policy administration point to provide it with a policy bundle. Basically, give me what I need as a PDP to make a decision on behalf of a PEP. And then, if we need additional data, we might be calling out to some external source for additional information. We can also let the policy decision point call out to a policy information point. A lot of lingo, but this is the basic setup. Again, the enforcement point is what we are in charge of in our code flow. But we delegate the responsibility for a decision to a PDP, the decision point. If everything works out, we'll be granted a green arrow to access the resource, do some action on that resource. So how does this all translate into, for example, handling a command? Well, we have a command. We have a token that is valid only inside of our network boundary, inside of our context. And this command is being processed by us in our code, in our enforcement point. We delegate the decision to the PDP. It takes action, or comes to a decision, and lets us process the command in our command handler if everything turns out okay. Now, you see this, there's a box around the PEP and PDP. They're typically co-located. Why? Because we have to have as a low latency as possible between those two elements. So in a Kubernetes environment, you'll typically have them in the same pod, 2 containers as a sidecar. So your application container is the PEP, and the PDP will be the open policy agent server. So they'll be co-located, and this will be present in every process. So if your service is actually multiple services, you'll have this set up for every service there. Okay, so we've seen what asynchronous communication means, what messaging entails, different message types, and how OPA can help us to achieve this on a structural level. How do we actually go about implementing this if we have all these elements available? So first off, a token typically, as in the synchronous case that we saw earlier, is very short-lived. Its expiration time is, well, short. Now, in our case, that won't work. Why? Because, again, our operations can be long-running. So we need to extend the expiration time for our tokens. Moreover, we can just do one token exchange right at the API gateway that I showed you earlier. We need to create or generate tokens for each message that we publish or send out. Again, to make sure that no one tampers with our message, we'll have to hash whatever data, whatever payload we'll include in our message. And we'll have that as a claim. That will be an attribute, just like any other claim. For example, who I am, my email address. And typically, we'll also have a message ID that we generate. So at the top, you'll have a stock change event, say. We have our data, product ID, current quantity, and a message ID that we generate. It will help us later, as I'll show you. That's our event. That is a raw event. That's the data that we want to transmit. And maybe this event is a consequence of handling another message before, a command that changed the stock, say. The token that we'll generate will look like this in a simpler format. We'll have the subject, that will be me, the user context or the identity context. It will include my, in this case, identity, my email address. We'll include the message, and most importantly, the message data hash. So we've hashed the data in the top code box that you see there, and we have included it in our token, which has then been signed. So the resulting event with the token will be pretty much like we had before, but we've added the token as well. Now, this token and this message, this event in this case, are bound. If for some reason this token were to be maliciously retrieved to be used in other messages, that won't work because we've bound it to this particular event and this payload. So it's useless in any other circumstance. So if we send out this stock change event with the token, how do we consume this token? So let's say that we have published this on a message bus or broker, and then we have one or more consumers consuming it and processing it. Well, first of all, we need to verify the token, just like we always do. We get the claims, the attributes that we'll need to use for access control. We'll first see, have we processed this message before? So for example, let's say that this event was somehow intercepted, and some attacker is replaying, sending us the same event again. We can use the message ID as sort of a check if we have seen this message before. It's no different really from how we approach at least once delivery. So you can think of it that way. So we can reject that event if we've seen it before, if it's maliciously replayed. Then, a super important thing. We'll see if the hash of the data in this event has been tampered with. If this check it doesn't turn out okay, we must reject the event. We can't consume it or process it because it might have been changed by some attacker. And finally, the whole reason why we're doing this is to make sure that we can then contact our policy decision point, our Open Policy Agent server, with the resource that we want to perform some action on and the claims that we have retrieved from the token. So again, the token, which we generate for every message that we want to publish, command, event, or query, will be bound to that message. So it doesn't matter if this token would be hijacked somehow, because it would be useless in any other case. So this is basically the mechanism that we need for zero trust, or enforcing zero trust, everywhere we have enforcement points, possible enforcement points in our async communication flow. And this works, again, for commands, events, and queries. So there are some things to consider if you actually want to implement this and employ it on a broad basis in your distributed system. For one, we're exchanging tokens or generating tokens for every type of message that we publish. Now, for low to mid-volume messaging, that could be fine. But when you start to reach a huge volume of messages that you need to publish, that can be tricky because you need to contact this authorization server to make sure that your new tokens are exchanged and generated properly. So there are some alternatives. You can use what's called self-signed tokens for this. This does require some certificate schemes that can complicate your implementation, but it's an option. Or this authorization server, this one instance that I've shown earlier that everybody talks to, could also be placed as a sidecar, as a side container in your pod, say. So you'll both have an Open Policy Agent server, which enforces policy and access control, and this authorization server to quickly create new tokens for this new event or command that you want to publish. Also, we've looked at operational workflows, meaning one service needs to indirectly communicate with some other service to trigger some business activity in the latter one. Not all processes or flows are of that nature. Some are more analytical. So for example, when I took the cab from the airport to my hotel, or rather the system, the Bolt system that I implicitly use, generates a price for me. How important is the user context there? Could be useful, or maybe not. Depends on what the analytical workload entails. So, yes, you want to enforce zero trust, but it might be less important in certain circumstances. But you should probably not avoid it entirely, but be aware that not everything is as enamored of this identity context that you propagate as you might think. Some scenarios are less demanding of having that identity context present. You'll see a bit more of this on the next slide. Event sourcing. How many have heard about event sourcing? Some of you. It means that we're storing events long term. We're basing all of our state in one bounded context, in one or more services in that context, on storing events and replaying them when we need to inside of that context. Now, typically, when you process events without event sourcing, you don't store events for a particularly long time. You have a window of events that you process, and after that, if some consumer enters the picture and wants to consume events, they're not available. You have to wait for any new events to be sent and then consumed. But with event sourcing, you're storing them potentially forever. What does that mean for your expiration? Well, you have to set it to a really long time. I mentioned that we need to extend it, and this time, what appropriately long time means is up to the actual application, but it needs to be set to such a time that if you replay this event stream a year from now, say, you can still do access control, so the token hasn't expired. Normally, this is not such a big deal because when you process an event inside of a context, you might, for example, send a notification via email. But you only do that once. If you replay the event stream a second time or a third time, you're not sending additional emails. You're maybe using the replay for other purposes, say building a view that you can query. So we're typically avoiding side effects when we replay these events. So again, the identity context will not be as important as the first time when you actually wanted to check, can this user send out an email to this target of email addresses? But once you've done that, you don't maybe need to check for that second or third time because you're not sending out those emails after that first time. So again, if you have these scenarios where the identity context is not that important, again, for example, for analytical workloads, you might not disregard, but downgrade the importance of me, the actual user, and exchange me for a system user or system role. How many of you are familiar with IAM in the cloud? You have users that invoke an action, for example, to deploy a Lambda in AWS. But that Lambda, when it needs to talk to a database, it will not use my credentials. It will assume a role to contact that database on my behalf, so to speak. We can have the same thinking here. We'll elevate a system role instead of my identity as the primary thing to check for. And this comes into play, for example, when we want to handle user removal. So let's say that I've been authenticated and authorized in some async flow, and we are replaying an event stream, but I have been removed from the system. I don't have an account anymore. Again, events are immutable, and if they're stored long-term, like with the event sourcing, my token, the information about me, will still be there, even though I'm not a user anymore in the system. My account is gone. So this is where a system role can probably be better. So it's an assumed role, and we'll check and do a zero trust enforcement with the system role instead of me. So again, this can come up when you have analytical scenarios, like determining a price, surging price, or with event sourcing. Can also happen if the background processing is not fast enough. So an event is published onto a broker, a consumer is expected to consume it right away, but for some reason it doesn't happen. So the token is still there, but I might be removed as a user. Then we need to handle it probably in this manner as well, through a system user or system role. And if I'm removed, we can also check this in our access control policy. So if you use this OPA Rego language, you can see that if I, as a user, am no longer part of it, the system, if I'm present in the user's removed array, well, okay, then access control cannot be enforced for me. This is a very special case, though, so again, I just wanted to provide the notion of sometimes zero trust and enforcing access control will occur for a system-level role rather than me, which is the sort of original user that we need to verify. And with that, that's all I had to say about the topic of access control and message-driven systems. Again, this can be tricky to implement, but it's mostly a conversation between you as application developers and your network administrators who work with security on their level. But there are some simple mechanisms you can implement to enforce zero trust. Hopefully you've got an idea of how to do it in this session. Thank you very much, and if you have any questions, please go ahead.